You've heard about Antarctica's research stations, but almost no one talks about what's happening on the other end of the planet. This is the Arctic, and it doesn't work the way you think. When you picture the North Pole, you might imagine something like Antarctica, cold, remote, maybe a research base with a flag stuck in the ice. But if you were suddenly dropped at the North Pole, you wouldn't be standing on land. You'd be standing on ice, floating on top of the Arctic Ocean. And that ice? It's moving. Let's put this in perspective. Antarctica is like a giant frozen continent. It's basically a huge rock covered in ice. You can drill into it and build on it, and the building will still be there next year. The North Pole is more like standing on a giant ice cube floating in a bathtub. Except the bathtub is the Arctic Ocean, and the ice cube is constantly breaking, shifting, and drifting around. That creates a problem Antarctica doesn't have. Antarctica has 55 permanent research stations. The North Pole, it has something else, and it works in a completely different way. It all started in 1937 when 4 Soviet scientists did something that sounded impossible and honestly insane. They flew into the middle of the Arctic Ocean, landed on drifting ice, and set up camp. They had no idea where they'd end up. They just let the ice carry them. 9 months and 2,600 kilometers later, they were rescued and became the first people to collect scientific data at the North Pole. That experiment would launch a decades-long obsession. If you can't build on solid ground, build on the ice itself. Today, that original idea, drifting with the ice, has evolved into something far more advanced. Russia's Severny Polus is essentially a self-sustaining Arctic base, built to drift across the polar ocean for up to 2 years at a time. At 83 meters long and 22.5 meters wide, it's roughly the size of a mid-range naval vessel, but with a very different purpose. The platform was built by Admiralty shipyards in St. Petersburg and features some of the most specialized cold-weather engineering on Earth. A double-reinforced aluminium alloy hull shaped to withstand the massive pressure of shifting ice sheets. A 15-laboratory internal layout allowing simultaneous research in oceanography, meteorology, biology, and atmospheric science. Autonomous life support systems, water treatment, fuel reserves, and food storage, enough to keep 48 people self-sufficient for months. A full satellite communication suite capable of transmitting large datasets in real time, even at high latitudes. It's also designed with ice-free zones and thermal regulation systems to prevent dangerous ice buildup on critical components. The ship doesn't resist the Arctic, it joins it. Once in the right location, engines are cut, and the platform lets itself freeze in place, drifting thousands of kilometers across the Arctic Ocean as a passive observer. The total cost hasn't been disclosed, but given its autonomy, instrumentation, and specialized hull, experts estimate it to be a 9-figure investment, putting it in the same class as high-end offshore platforms or advanced naval vessels. Russia currently operates 2 platforms, North Pole 41 and North Pole 42, and despite political tensions, they've opened participation to researchers from India and China, positioning these platforms as diplomatic and scientific tools alike. France's station takes a different approach, smaller, more agile, and built around sustainability. The Tara Polar Station is just 26 meters long, but it's a floating lab designed to survive 500 days locked in Arctic ice without relying on fossil fuels. It's powered by a hybrid system that includes solar panels for continuous daylight periods, wind turbines designed for polar gusts, biofuel generators for energy security during low sun months. Its standout feature is the moon pool, a vertical access shaft through the hull that allows scientists to lower instruments directly into the ocean without ever stepping outside. Construction was handled by 200 specialists at Constructions Mécaniques de Normandie, requiring over 150,000 hours of labor and extensive cold weather testing. The station's hull is designed to flex slightly with ice pressure, using a specially engineered frame and buoyant substructure to reduce stress. While the final cost hasn't been published, that kind of labor, material, and custom engineering puts it easily into the tens of millions of euros, particularly given its experimental nature and cutting-edge sustainability profile. Germany took a different route. Rather than build a floating platform, they turned an existing icebreaker into a full-scale Arctic base. In 2019, the Mosaic expedition deliberately froze the RV Polarstern into Arctic sea ice and let it drift for a year to experience the full seasonal cycle from inside the polar system, turning the ship into the core of the largest polar science operation in history. The expedition budget, €140 million, about $150 million, and it funded one of the most logistically intense science missions ever attempted. Ship operations and fuel to power the Polarstern and its support fleet, over 80 resupply flights to drop off fuel, food, equipment, and emergency aid. Support for 600 researchers from 17 countries rotated in and out over 12 months. Dozens of temporary ice labs constructed around the vessel, forming a full scientific camp directly on the moving ice. The challenges were constant. The ice cracked underfoot, swallowing equipment overnight. Entire research zones had to be relocated on short notice. Scientists used snowmobiles, tracked sleds, and satellite-guided mapping to monitor drift and cracks. But the result was unprecedented. 150 terabytes of data on Arctic climate, ocean currents, atmosphere, and sea life, now referenced in over 300 scientific papers, many of which are shaping the next generation of climate models. It wasn't just a research project. It was a $150 million engineering experiment in surviving and thriving in one of the most unstable environments on Earth. But long before Tara or Polarstern, the United States was already building drifting Arctic stations directly on the ice. In the 1950s through the 1970s, the US operated several floating research stations that pioneered many of the construction methods still used in Arctic science today. The most famous was Fletcher's Ice Island, or T3, a massive natural ice floe the size of a small city. Roughly 7 miles long, over 200 feet thick, and stable enough to support aircraft landings, it became a mobile base that drifted across the Arctic for 26 years. To make it work, engineers built prefabricated labs and shelters flown in and assembled on site, a diesel-powered grid for heat and electricity, a runway carved directly into the ice used by C-47s and C-130s, flexible foundation systems to cope with shifting and cracking ice. Other projects like ALICE-2 and Station Alpha used similar methods, with ALICE-2 assembled in just 22 days by airlifted components and modular cold weather structures. While they've been gone for decades, these stations introduced rapid deployment modular systems, air-based logistics for remote polar ops, ice-adaptive engineering techniques, and insulation, power, and comm strategies that are still used on today's drifting platforms. Eventually, the US pulled out, largely due to rising costs, shifting priorities, and the rise of satellite observation. But some countries took a different path. They went for permanence. If you can't build on the North Pole, you build as close as possible. And that's exactly what happened in one tiny frozen town in Svalbard. Welcome to ny-ålesund, a former coal mining outpost transformed into one of the most remote and advanced research hubs on Earth. At 78 degrees 55 minutes north, just 1,000 kilometers from the pole, it's now home to an entire village of miniature space programs, each one built to survive and study the Arctic year-round. In 1916, ny-ålesund was built to mine coal. It had underground tunnels, a harbour, a power plant, and permanent housing, all constructed for heavy industrial use in brutal polar conditions. After a deadly mining explosion in 1962, the site was shut down. But in 1968, Norway did something no one expected. They converted the ruins into a year-round research base. Mining buildings became labs. Housing blocks were retrofitted for researchers, power and port systems were upgraded, but building anything permanent here requires extreme adaptation. Every building in ny-ålesund is constructed with cold climate engineering in mind. Elevated steel stilts to avoid thawing the permafrost below, triple glazed windows and vapor barriers to trap heat, flexible pipe systems that shift with the freezing ground, specialized cold weather concrete and insulated cladding for storm resistance. Even the town's utilities, water, power and data are routed through heated underground tunnels to prevent freezing. Today, ny-ålesund houses 14 research stations from 10 countries, representing over 100 institutions from more than 20 nations. Outposts Research Base, Germany and France, is the flagship station in ny-ålesund and a masterclass in cold climate modular design. Built from expandable pods like a polar space station, features triple-wall vacuum insulation, effectively turning the station into a human-sized thermos. Has clean rooms with contamination controls stricter than most hospitals. Outposts also maintains the dramatic Zeppelin Observatory, a facility perched 474 meters above sea level, only accessible by cable car even in minus 40 degrees Celsius weather. Underground heated utility tunnels connect all systems, while its 30-meter atmospheric towers continuously monitor some of the cleanest air on Earth. But Germany and France aren't the only ones turning Arctic engineering into a statement. On the other side of the settlement, China built something radically different and did it in record time. Built in just 76 days, the China's Yellow River Station was prefabricated in China, shipped 8,000 miles, and airlifted by helicopter to the site. Its construction includes pagoda-inspired design adapted for Arctic storms, steam-injected pile foundations to anchor it deep into permafrost, traditional Chinese architecture merged with steel Arctic engineering, a cultural megabuild in one of Earth's harshest environments. While China brought speed and symbolism, South Korea focused on precision and automation. The Daesan Station is one of the most technologically advanced facilities on site. Fully automated life support systems monitored remotely from Seoul. Heat recovery ventilation captures waste heat from people and equipment. Designed to withstand both Arctic conditions and seismic activity. Features modular labs that can be reconfigured for new missions. And an advanced waste management system, because nothing can be left behind in Svalbard. Just a few steps away, Japan took Arctic engineering in another direction entirely, one defined by scientific sensitivity and raw atmospheric data. Where Korea built a high-tech outpost, Japan built a fortress for precision atmospheric research. The Raben Station houses sensitive air intake systems capable of detecting molecules in parts per trillion. Structures are windproof to withstand 200+ miles per hour Arctic gusts. Instrument bays are climate-sealed to maintain micro-calibrated measurements. Atmospheric towers look more like sci-fi antenna arrays than scientific instruments. But ny-ålesund isn't just a place for atmospheric science. It's also a front line for marine biology. And that's where the UK comes in, with a station built to bring the Arctic Ocean indoors. UK's NERC Arctic Station is focused on marine research. Includes heated seawater systems that carry Arctic Ocean water through labs for real-time analysis. Hosts a diving operations facility supporting under-ice science missions. Has mechanical launch systems to deploy small boats into ice-covered waters, even in sub-zero storms. All of it engineered to keep living marine organisms alive and data flowing in an environment designed to freeze everything solid. Despite its remote location, ny-ålesund operates with the precision of a miniature polar city. Power comes from a centralized diesel-based grid which not only keeps the lights on, but also feeds a district heating system that circulates warmth through insulated pipes to every building. Redundant generators stand ready in case of failure because out here, even a few hours without power could be catastrophic. Supplies arrive either by air, using a gravel airstrip capable of handling twin otters and helicopters, or by sea during a narrow summer window when ice conditions allow supply ships to reach the harbour. Outside of those months, everything has to be carefully stockpiled. Every litre of fuel, every kilogram of food, every scientific instrument, all of it has to be flown or shipped in and logged with military precision. And every station here has to follow Norway's strict environmental regulations. Waste isn't buried or burned, it's packed up and removed from the island entirely. Buildings are designed for zero long-term impact on the tundra. Even minor disturbances to local wildlife are avoided at all costs. The settlement runs like a closed ecosystem, as if it were on another planet. Outside, danger is always present. Polar bears outnumber people in this part of Svalbard, and they don't fear humans. That's why rifles are standard issue. Anyone leaving the settlement boundary is required to carry one, not as a threat, but as a last resort. The costs of running ny-ålesund are as extreme as the environment. Fuel alone runs into the millions each year. Keeping a technical and scientific staff operating year-round takes tens of millions more. Maintaining infrastructure, running logistics flights, repairing equipment in the dead of winter, it adds up fast. And that's before you factor in the construction itself. Building a basic Arctic research station here can cost upwards of $10 million. The more advanced facilities, like the German-French Auerpev base, can cost $50 million or more. Just flying to Svalbard can cost thousands per person. And yes, a single meal here might set you back $50. But ny-ålesund isn't the only way countries have secured a foothold in the Arctic. Beyond this international hub, several nations have gone a step further, building permanent stations of their own in some of the harshest conditions on Earth. Let's start with the United States and its most remote research site in the Arctic. At the summit of Greenland's vast ice sheet sits Summit Station, operated by the U.S. National Science Foundation. It's the highest Arctic research base in the world, located over 3,200 meters above sea level, and one of the most isolated. There's no road, no runway. The only way in or out is by ski-equipped aircraft. Built on compacted snow and shifting glacial ice, the station uses modular elevated buildings that flex with the moving surface. Supply runs are so difficult that parachute drops are often the only option. And despite the challenges, this tiny US outpost supports some of the world's most important climate research, analyzing ice cores that stretch back over 110,000 years. The cost of operating here? While exact figures vary, every kilogram of supplies costs hundreds of dollars to deliver, and the base is managed under an ongoing multi-million-dollar program by Battelle Arctic Research Operations. Then there's the Utqiagvik Observatory, farther west in northern Alaska. This U.S. facility sits in the cloudiest, coldest corner of the state, enduring 67 days of complete darkness every winter. Here, engineers built permanent structures on permafrost-resistant foundations and wrapped them in multi-layer insulation. But what makes this station unique is its partnership with local Inupiat communities, blending traditional ecological knowledge with cutting-edge satellite monitoring. In 2020, it received a $3 million NSF grant to develop a hybrid sensor network combining cultural heritage with Arctic science. Next, head to Canada, where one of the world's largest investments in Arctic research infrastructure has taken shape. In 2019, the Canadian government opened the High Arctic Research Station, CHARS, in Cambridge Bay, a $250 million facility designed for year-round operation. It's not just a research lab. It's a climate-controlled Arctic campus, powered by hybrid energy systems and built with modular expansion in mind. The site includes high-tech labs, community integration spaces for Inuit collaboration, and deep pile foundations engineered to resist thawing permafrost. CHARS supports 44 scientists year-round, a scale unmatched in the Western Antarctic, and stands as both a scientific and strategic statement of Canada's northern presence. Then there's Denmark and its outposts at the literal edge of habitability. Willem Research Station, located at Station Nord in northeastern Greenland, is just 924 kilometers from the North Pole. It was inaugurated in 2015 after a €9.3 million investment from the Willem Foundation. But what's astonishing isn't the cost, it's the strategy. With supply ships arriving only once every 5 to 10 years, the entire facility is built for total self-sufficiency. Warehouses store years' worth of supplies. Every system has a backup and a backup for the backup. And researchers rotate on 26-month shifts, often spending 2 Arctic winters before heading home. Here, survival isn't a challenge, it's the blueprint. And finally, there's Sweden, home to the oldest continuously operating Arctic station in the world. The Abisko Scientific Research Station, established in 1903, has evolved from a remote field camp into a world-class facility focused on atmospheric and aurora research. Unlike most Arctic bases, Abisko is reachable by public transport and sits within a nature reserve north of the Arctic Circle. In recent years, Sweden has modernized the station with geothermal heating, low-energy ventilation and upgraded labs, all while preserving the original wooden buildings from over a century ago. It's a rare example of Arctic infrastructure that balances modern science with historical legacy. These aren't just research stations. They're footholds, anchors in one of the most hostile, remote and unpredictable environments on Earth. From the drifting labs of Russia to the precision instruments of Japan, from Greenland's ice summit to Canada's billion-dollar Arctic campus, each one is part of a quiet race to study, to survive, and to stay. Because in the Arctic, building anything is hard, but staying, that's even harder. Thank you for watching, and if you want to see more of the world's most extreme construction, from bunkers to bridges to bases like these, make sure to subscribe. We've got a lot more coming.